Okay, let's get started. Good morning. Okay, that was bad. Let's try that again. Good morning. Good, good. Much better, much better. Okay, so exam is this Thursday. There shouldn't be any shocker to anyone. Same place as last time, same time, same seating location. Just like last time, look for your TA when you get there. If you can't find him or her, look for me. I'll be on the stage. Okay? And I mentioned last time I'm participating in this Relay for Life fundraising thing. We officially start today. The last day we collect is October 30th. The little pouch is in the front of the room. It says Relay for Life on it. Okay? So any kind of donation will be appreciated. It's a very worthy cause. It goes to American Cancer Society, do cancer research and looking for treatment options and the cure, ultimately. And thank you if you're donating. Okay, so today we're going to continue section 3.9. More related rates examples. And as just like what we talked about last time, this section will not be on exam 2. And Wednesday in class, we'll do a review for exam. I'll do what I did last time. I'll prepare some examples that I think are relevant to your exam and then work as many of those out in class as we can. So basically what we'll be doing is pretty much the same as last time. More complicated examples this time, but along the same line, trying to relate some quantities' rate of change to some other quantities' rate of change. We'll start with this example. Two cars start moving from the same point. One travels south at 60 miles per hour, and the other travels east at 25 miles per hour. And obviously the distance between those two cars, the line of sight, is something that's going to be changing as time goes on. We are interested in finding the rate of change of that distance between them at the moment 2 hours after this whole thing started. Okay, so once again, I start from the same point. One goes south, one goes east at different speeds. We're looking for the rate of change of the distance between them at a particular moment. As usual, let's make a sketch of what's going on here. Let's say here's where we start. And sometime later, one of the cars is down here. It moves south, right? We'll call this car A, the one that moves south. And the other one is the one that moves east from that point. And somewhere over here, we'll call that car B. So I'll call this guy A, and we'll call this guy B. This right here is the distance from car A to the starting point, and this right here is distance from car B to the starting point. This line right here, that's the distance between the two cars, and that's the quantity that's going to be changing just like the other sides. And we're interested in how fast that long quantity is changing, the hypotenuse of that triangle. Okay? Okay. Okay, so we got this triangle going on here. That's B, that's A. Let's get some labels on here. Let's call the distance from the starting point to car B, we'll call that X. And we'll call the distance of car A from the starting point. We'll call that y. Call them whatever you want. X and y seem to be pretty obvious choices. And alongside here, the hypotenuse, let's call that z. And obviously, all three of these things are changing with time. Okay, so let's collect the information we know and then find out what we want to know. Let's read the problem again. Two cars start moving from the same point right here. One travels south at 60 miles per hour. That means that the rate of change of this quantity y is 60, right? That's how fast y is changing. There we go. That's our speed of the car, the one that went south, car A. And similarly, dx dt is 25. Okay? What do we want? So what mathematical quantity are we looking for here? dz dt when, at what moment? T is 2, okay. So that's assuming that t is equal to 0 is when we start. Okay, so that's a very, very natural starting point to go. Okay. All right, so we collect the information we got here. We kind of, once we got this picture and the stuff we're looking for, we're just solving a very simple geometric problem using related rates and implicit differentiation sometimes that happen to solve the practical problem we're looking for. All right, so here's a triangle. Here's what we know, and that's what we want. Okay, so we're trying to relate dy dt, dx dt, and to dz dt. We're trying to relate the two car speed to the distance, to the rate of change of distance between them. And the relationship between all three variables, knowing this is a right angle triangle, is something we know, right? We know that z squared is going to be x squared plus y squared. The Pythagorean theorem gives us that. Let's take the derivative with respect to time. Here we're going to use implicit differentiation. Derivative would be on the left side is 2z. And now you got to remember z is a function of t. So taking the derivative involves a chain rule, dz dt. Same thing with x and y. They're both implicit functions of t. So derivative of x squared would be 2x dx dt. And derivative of y squared would be 2y dy dt. Okay, make sense, everyone? Good. We're interested in dz dt, so let's divide it by 2z on both sides. Notice that 2 doesn't matter. We can cancel the 2 all the way through. or equivalently divide everything by 2. Left side on the top, right side on the top would be x times dx dt plus y times dy dt. Downstairs, we're dividing by z. And as usual, you only plug in any number after you take a derivative. Do not put any of those numbers in, the 25, the 60, all those things, into anything until you've taken one derivative. Once you've gotten a derivative, now you can plug in anything that you have. Okay, so we know dx dt is always, 25, right? That's not changing. We know dy dt is always 60, and that's not changing. Besides those two numbers, if you look at my expression for dz dt, I also need x, y, and z. Okay, so at the moment when t is equal to 2 hours after we have started doing this, what would x be? And how do you find it? 30? And how did you find that? 50, right, and that's from the speed, right? Yeah, 50. So that's 25 miles per hour 2 hours later. You start from the same point, so initial distance is 0. You move at 25 miles per hour, you move 2 hours, so that's 50. And y is therefore similarly 120, right? It's moving at 60 miles per hour, move for 2 hours, so that's 120. If you know x and y, then z you also know. From the Pythagorean theorem, we know z is square root of 50 squared plus 120 squared. Plug all of this stuff into this expression, and we should be good. 50 dx dt, y dy dt, all divided by z. Putting this into a calculator, we get, rounding this number, it turns out to be around 65. Okay, so that's how fast the distance between two cars is increasing, 65 miles per hour, at the particular moment. That's 2 hours after we've started this whole thing. As time changes, this 50 is going to change, that 120 is going to change, downstairs is going to change. So at a later time, we should be expecting a different rate of change, because what x, y, z are changing, but dx dt and dy dt are not changing. Questions on this example? Okay, now let's look at a slightly more difficult one. Got an airplane here flying horizontally at a fixed altitude of 1 mile. And it's going at a speed of 500 miles per hour. You got this observer on the ground that's watching the airplane. And we're interested in finding at what rate is the angle between the line from the observer to the airplane and the ground changing when the airplane is 2 miles from the observer. If you're outside, you see an airplane flying over you. If you point your finger at it and you follow the airplane, notice that your arm is going to form an angle with the ground. And that's going to change as the airplane moves around. And that's the rate of change of that angle is what we're looking for here. If this observer were a radar station, for example, and that's the kind of a rate of change that if you were designing how the radar should be pointing, that you need to know how that's changing. Okay, once again, let's sketch out what's going on here. Here's my airplane. It's a dot, but it's representing the airplane. It's moved at the altitude of 1 mile. So let's say this is the ground. So right here, this is 1 mile. We'll use 1. Be careful with units when you do your homework. A couple of the problems have units all mixed around. All the examples I have prepared here have consistent units. But on your homework, be sure everything has the same units. You may have centimeters and meters. Change everything to the same thing. Doesn't matter which one, and work with those numbers. And that dot here is representing the observer. This is the line of sight from the observer to the airplane. Another triangle. Triangle is a very, very common thing that's going to show up in all of these related rates problems. Some kind of triangle. Okay, so this line of sight forms an angle with the ground. Let's call that angle theta. Let's label a few things here. Let's label the distance from the point directly below the plane on the ground to the observer, this ground distance right here. Let's call that thing x. And let's call the distance from the observer to the airplane, we'll call that y. Okay, let's sketch a picture, simplify what's going on here. Label your size, reduce this to a geometry problem with implicit differentiation and chain rule. Okay? Get a geometric figure in front of you and just work with that. And that one's already pretty simple, but we'll make it even more so, like this. The opposite side to the angle is not changing. The airplane is always moving, always flying at 1 mile altitude. Okay, now let's find out what we know. The height is 1 mile, we already got here. The speed is 500 miles per hour. And remember, this airplane is flying horizontally, like this. How would you mathematically represent this number, 500, using the quantities we have on our page here? dx dt, good, very good. dx dt equal to 500, right? What if the airplane were approaching the observer? What would that be then? That would be negative 500, right? Because the distance directly below the airplane to the observer is then shrinking. Here it's increasing. dx dt is a positive rate. Now, what mathematical quantity are we looking for from this problem? What is the problem asking? At what rate is the angle between the line, blah, blah, blah. So how would you represent that mathematically? d theta dt, good, good, good. When what happens? Good. When y is equal to 2. Okay, so look, at what rate is the angle? The angle is our theta. At what rate? Rate is a derivative. What is the derivative of the angle, d theta dt? at the moment when the airplane is 2 miles from the observer. 2 miles. Y is equal to 2. Once again, I already made sure the units agree. If you're doing this on a homework problem, I think like I said, some of them have units all mixed up. Make sure everything is consistent. All right, so now we got a simpler problem here. This triangle, x, y, and xy are both changing, and theta is also changing. X, y, theta are functions, implicit functions of time, right? As time goes on, the only thing that's staying constant is that 1 mile, but x, y, and theta are always changing. And as you can see, as this is fixed, but x and y are both increasing, then the angle will get smaller and smaller. When the airplane is very far away, it'll be practically at the same height as the horizon from the point of view of the observer. Okay, let me just sketch that here again so we can work with it. Theta x, y, 1. Ultimately, we have to relate the rate of change of x that we are given to the rate of change of theta that we want to find. That means we have to start with how x and theta are related. What's a good way to relate those two things? Sine and cosine, okay. But if I use sine here, so sine actually only relates y to theta, right? Sine is the opposite over hypotenuse. So sine is not going to work. Secant, let's see, secant is cosine is, let's see, adjacent over hypotenuse. That's got x and y mixed together. The problem with cosine is I don't know the rate of change of y, right? If I use cosine, so let me jot that down. Those are good ideas, actually. If we use cosine of theta as equal to adjacent over hypotenuse, then we need dy dt after we take a derivative. But we don't know that. We might be able to solve for that, but that's an extra layer of complexity that if we can avoid, that would be great. So is there a way to relate x and theta without getting y involved? Tangent, absolutely, tangent. Tangent is the opposite over adjacent, right? Of course, cotangent is also fine, but just as long as here as long as we only relate what we know, directly know, to what we want, without getting an intermediate variable involved. Once you got here, what follows is actually relatively easy. Let's take the derivative. Derivative of tangent is secant squared. What else do I need? If I'm taking derivative with respect to t, chain rule, d theta dt. Theta is an implicit function of t, so if you differentiate with respect to t, you get secant squared theta. And then, because theta is something more than just a t, but ultimately depends on t, remember to attach the d theta dt. Right-hand side, think of this as x to the minus 1. When you take the derivative, you get negative 1 over x squared. And once again, x is also an implicit function of t. So we have to, again, attach dx dt. Okay, let's solve for what we want. The theta dt is now negative 1 over x squared dx dt over secant squared of theta. That is equivalent to negative 1 over secant squared is a cosine squared. So cosine squared times that All right, so now we've taken the derivative. We plug in what we know. Once again, derivative, then you plug in stuff. At the moment when y is equal to 2, that's the hypotenuse. Right? The problem says look for d theta dt at the moment when y is equal to 2. This time we're not given exactly when that happens. We're given at the moment when y is equal to 2. Look at what you need in your expression. You need cosine of theta. Cosine depends on adjacent. You also need x. But once we know x, we know cosine of theta. So we got to find our x. And this is pretty simple. We have a right angle triangle. You know two sides. You know everything there is to know. Pythagorean theorem says that hypotenuse squared is equal to the sum of the squares of the other two sides. So therefore, x must be equal to, let's see, radical 3, right? Okay, now we got everything we need. We can find d theta dt, negative cosine. Cosine is adjacent over hypotenuse. Radical 3 over 2. Right? Cosine is adjacent over hypotenuse. This guy right here, adjacent. Hypotenuse squared. Over x squared, radical 3 squared, times dx dt. And dx dt is what, 500, is it? Yeah. Okay, now I just have to clean this up. And again, I'll round this a little bit. Turns out to be minus 125. The units would be radians per hour. Hour because that's how we measure our time in this problem. And radians, remember when in calculus, you're always dealing with an angle in radians. Almost never are you dealing with an angle in degree. Even when you do, you're dealing with that indirectly. You want to change it to radians. That's a rate of change of an angle, so it will be how you measure the angle per unit time. And then we're using, like I said, hours. Questions? Okay, good, good. All right, let's make it more interesting here. This is very similar to one of your homework problems, but I tweaked it around a little bit. If you could follow along here, you should be able to make the necessary change when you deal with a similar homework problem. Here we got this ladder that's leaning against the wall, and of course the other end is on the ground. And the top of this ladder is sliding down, but staying on the wall. So when that happens, because the ladder's length cannot change, the bottom of the ladder must also be sliding away from the wall. And we know here that the top of the ladder is sliding down at the rate of 0.15 meters per second. At a particular moment when the bottom of the ladder is 3 meters from the wall, it is sliding away from the wall at the rate of 0.2 meters per second. Okay, that's how fast it is sliding down. That's how fast it's sliding away from the wall. Based on the information given here, we want to find how long is this ladder to begin with. Again, we're assuming the ladder cannot change length. It's a fixed ladder with these kind of situations going on. Picture. Here's my wall, here's my ground. Green line is representing my ladder. So what happens here is as the ladder slides down, the top of the ladder slides down, the bottom of the ladder slides away too. So sometime later, the ladder is going to look like that, right? The length cannot change. Based on what we know here, how fast the top is sliding down, how fast the bottom is sliding away, we can find out how long this ladder is. Okay, so let's simplify this picture a little bit. Just look at one particular moment of the situation, just one moment. Let's look at this part right here. There's my green ladder. Now we label sides. Common theme here, you sketch a picture, assign variables, and then reduce it to a geometry problem, right? Find out what you know, and then find out what you want to know. I'm just going to be very, very creative and use X, Y, Z. X here is going to represent how far the bottom of the ladder is from the wall. And again, all the units here agree, meters and meters per second and all that stuff. As long as that's the case, you can ignore the units as you work out the problems. So if you're given a problem, the units are not consistent, always make them the same before you do anything. Y here is representing the distance from the top of the ladder to the ground. Top of ladder to ground. And Z is just how long the ladder is. X and Y are changing, but Z is not changing. That's how long it is, it cannot change. Z is a constant, which means if you ever encounter the derivative of Z as you work out a problem, that's going to be a 0. It cannot change. Okay, now we collect information. We know, let's see, what do we know? We know the top of the ladder is sliding down a vertical wall at 0.15. So how do we represent that piece of information mathematically using the variables we got? Top of the ladder sliding down. dy dt, good, equal to? Good, negative 0.15, right? Because that distance y is decreasing. It is sliding down. At a later time, the top of the ladder to the ground will be a smaller distance. It must be a negative rate. The bottom of the ladder is sliding away from the wall, so that's a positive rate. dx dt is equal to 0.2. Good. Now what we want is actually very simple. How long is the ladder? Well, that's z. And by the way, we know these happen when the bottom of the ladder is 3 meters from the wall. X is equal to 3. Another triangle dealing with 3 sides, so we have a bunch of different tools. We're not dealing with any angle here, so cosine and sine and tangent, they're probably not going to help us. They tell us something about the angle and all that. We're only dealing with the 3 sides, so that means the Pythagorean theorem is usually the best way to start. Okay, so Pythagorean's theorem says z squared is x squared plus y squared. Now we differentiate time with respect to time. Remember, z is a constant. When we take the derivative of that, we're going to get a 0. The right-hand side, x and y both depend on t. So the chain rule, when you take the derivative, remember to use the chain rule. 2x dx dt. Y squared gives you 2y dy dt. Now we can plug in what we know. By the way, let me resketch my picture here. X, Y, Z. Ultimately, this boils down to when x is equal to 3, if we can find out what y is equal to, we know z. Right? If I know at the moment when x is equal to 3, if I can somehow find out y, then z is automatically found because of the Pythagorean theorem. And that's what this equation is going to tell us. This equation will tell us what y is equal to. Using that information, I can find z. Okay, let's solve for y. Well, let's just plug in stuff we know. You don't really have to solve for anything. Explicitly, plugging dx dt, whatever that's equal to, 0.2, dy dt, negative 0.15, and then x is equal to 3, right? Therefore, z is equal to 2 times 3 times 0.2 plus 2 times y, that 2 really doesn't matter, times negative 0.15. The only thing you don't know in this equation is y, and that's easy to solve. Y turns out to be 4. And now you know at that particular instant, x is equal to 3, y is equal to 4. Z is equal to, it's a 3, 4, 5 triangle, or you can use the Pythagorean theorem. But we would know z is equal to 5. So this one's a little bit different. We were looking for one of the sides, but we kind of have to work around that using the rates. Notice that z, the quantity we're looking for, actually disappeared here. We're solving for that indirectly after we took the derivative. But then once we know y, and of course x, we know z. Okay? Okay, this last example is probably the most difficult one. But the tool we need, namely similar triangle, we already saw last time. So we're halfway to how to solve this problem after last time. You got this trough here that's 16 feet long, 16 feet. And its ends have the shape of isosceles triangles that are 3 feet across the top and have a height of 1 foot. Let me sketch that. So we got these isosceles triangles on the ends, and it's a 3D trough here. All right, so it's like those chocolate bars you see. What are they called? Those triangular ones? Yeah, that's right. That's the one. It's that shape here. There's no top here. Water can get in. So this is 16 feet long, right? And then the height of these isosceles triangles, 1 foot. Obviously, this is not to scale, but you get the idea. And they're 3 feet across the top, right here, 3. We're filling this thing with water. So this green part is going to represent the water that's already in the trough. If the water level is rising at 3/16 feet per minute when the water depth is 2/3 feet, how fast is the trough being filled? I want to sketch the view we would get if you were looking at this from the side. Just looking at this with the depth into the slide here. We would see the isosceles triangle, of course. And then the watering here. I want to cut this in half. So here's my water. Let's just work with half of those. The problem says that the height of this isosceles triangle is 1. So this is equal to 1. 3 feet across the top. If I chop this in 2, so this is 3, right? If I chop this in 2, then this guy right here must be 3/2. As the water rises, notice that half of that is still going to be a triangle. Let's call the height of that h. So h, height to water level, water surface. And then x is just going to represent the width of that water surface. Now let's think about how much water is in here. to find the volume of that green part here, the green part of that's water, and the volume, you have to find the area of the triangle times 16. Just like how you find the volume of a cylinder. The area of the triangle times 16 for how long it is. Volume of water is equal to area of green triangle. Okay. Times 16. 16 because it's 16 feet deep into the page. Okay, the green triangle, here's half of that. Remember, triangle area is 1/2 base times height. So this is 2x. The height is h. So this triangle is this guy right here. One half base times height, 1/2 base height times 16 feet deep into the picture. (16xh) is what we end up getting. Okay? All right. Now we can find out the stuff we want. Oh, by the way, eventually we're going to have to relate x and h. We've done this last time. By similar triangle, we can actually relate x and h. Similar triangles, we know x over h is going to be 3/2/1. Right? So that means x is equal to 3/2h. Okay, let's go to the volume equation. Volume is 16xh. So that is 16 times x times h, right? So that's 24h squared. All right, so what do we know? We know, what is it? The rate of change of the volume. Sorry, we don't know that. That's what we want. We know the, what do we know? How fast water level is rising. We know dH dt. Water level is rising at the rate of 3/16 feet per minute. At the moment when h is 2/3. And we're looking for how fast we're filling that thing. So how fast is the volume changing? Okay, and look, I want to relate the rate of change of h and v. I already got an equation relating v and h. So that's one step later. Differentiate with respect to t. We get dv dt equal to 48h dH dt, because h is implicit function of t. Now we're plugging stuff. I've taken derivative. I can plug in anything I want. So I plug in at this moment when h is 2/3. dH dt is 3/16. And this gives me 6. Volume per time, so cubic feet per minute. All right, that's it for today. And Wednesday we'll do review in class. Okay, so I'll prepare problems and do that in class on Wednesday. See you Wednesday.
I have a question. Are you teaching math 261 next semester?
261, no, I'm teaching 162.
Oh, okay. Wait, is that?
That's the one right after this one.
It's called. Oh, okay.
So usual progression is 161, 162.
Yeah, then I got confused. So you will be teaching 162, you said?
I will
Okay, and at the same time.
at the same time.
Thank you.
Best time.
Possibly change change recitation classes, like
Change recitation.
yeah.
At this point, it will be difficult, but
It's only because I seem to be in this recitation where there's a lot of kids are taking Calc 4, and then one person has it, they get harder quizzes.
no, don't worry about it.
I don't know.
Saying that it's not.
I do well in the exams, which means I'm learning
Yeah,
in
and
class.
that's all that matters.
It's just that it's starting to weigh down my GP. It's starting to weigh down my grades in class. It's kind of.
Now, if you continue doing well on the exams, then that's only going to be a very small part of it. But you know what? Will you write me an email and just write down whatever you just said to me, and I'll show it to the TA, and I'll hide your name.
It's not a